So do an example problem for a single walled section. So the first of the problem asks us to estimate the shear stress in each wall thickness when the applied torque is 50 kip inches. Okay, so we want to find what is tau in this case. All right. So the second part is asks us to find the angle of twist for the section. So that would be find phi. So so we know that tau is as a function of s is going to be equal to our torque, overall torque, divided by 2a t. So we defined it in earlier in this section. Okay, so t is a function of s. Right. So but our a is constant, and our t. So the only thing that's changing is our t, our thickness along our section. So the torque was given to us as 50 kip inches. The area we need to calculate. So to calculate the area, we're gonna take it's just gonna be the width of the section times the height. So the width of our section would be equal to 8 inches minus, minus, whoops, that should be a 1/4 inch, minus a 1/4 inch divided by 2 minus a 1/2 inch divided by 2. So we're taking we're trying to find the center point along our tube section here for our average to find our average area. Okay. So for the height, the height would be equal to 6 inches minus 1/4 over 2 minus 1/4 over 2. Right. So if we multiply this out, what we end up getting is we get 43.8 inches. Okay. All right. Inches squared, I should say. Sorry. All right. So so now we have the area. The only thing that would vary along the section is the thickness. So along the beam we have 3 walls that are 1/4 inch thick. So they would all have the same shear stress. And we have one that's 1/2 inch thick. Okay. So for the 1/4 inch section, we would end up getting 50 kip inches over 2 times 43.8 inches squared times 0.25 inches. So this would give us a value in kpsi. So we would get 2.280 kpsi. And then if we repeat the process for the 1/2 inch thick piece, you would get you would just have the same torque, the same area. The only thing that would be different is we would have the only thing for the 1/2 inch section is that we would get we would put the 1/2 inch on the bottom, and since it's twice as thick, the shear stress would be half as much. All right, so that was the first part of the problem. The second part of the problem asked you to determine what is the angle of twist. So for the angle of twist equation, we defined as being equal to the torque times 1 plus the Poisson's ratio divided by 2 a bar squared, right, times the integral of 0 L ds T of s. Okay, so I'm confident that these are all these terms here. We were not given in the problem description. We weren't given the Poisson's ratio. We weren't given the elastic modulus. But if you were asked to determine the numeric value of the angle of twist, you would need to know those. You would need to know those numbers. Those would be provided to you on like a quiz or in your homework. But in this example problem, we're not really focused in on that because I know that you all can do that part of the problem. So we're gonna just focus in on the integral part of the problem. Okay, so how we so we're really interested in is how do we calculate this integral? So the integral from 0 to L ds T of s. All right. So what we're going to do is we're going to break up our section here into 4 different walls. We're going to start on the bottom left of our corner to here to the top left. We're going to call this section 1. From the top left to the top right, we're going to call this section 2. From the top right to the bottom left, we're going to call this section 3. And from the bottom right to the bottom left, to go all the way around, this should be section 4. Okay. All right, so that's what I'm going to, so we're going to break up this integral to integrate from 0 throughout the whole perimeter. We're going to break this into 4 separate parts. We're going to calculate the part of the integral for side 1, the part of the integral for side 2, the part of the integral for side 3, and the part of the integral for side 4. So we'll start with side 1. Okay, so T of s is constant along side 1. It's equal to 1/4 of an inch. So we could bring it outside of the integral. And then the integral of ds is just going to be the length of S1. Okay? So this is the length of S1, which is would be equal to the 6 inches minus the thickness of the top and the bottom section. So the top section is 1/4 inch thick and the bottom section is 1/4 inch thick. So we would just have to subtract 1/4 inch 2 times. Okay, so that's the integral for S1. For S2, it's again 1/4 inch thick. So we can bring that out, and then we have the length of S2 would be 8 inches minus I'm sorry guys, it should be an 1/8 of an inch, not 1/4 of an inch. Sorry, it should be half the thickness, not the full thickness. Then for S2, it's 8 inches long minus the thickness of the 2 sides. So you'd have the left-hand side would be 1/8 of an inch to the center of the wall, and the right-hand side would be 1/4 of an inch from the center of the wall. All right. And we could then repeat the process for side 3 and for side 4. So if we repeat the process for side 3, again, side 3 is 1/2 of an inch thick. So we have to put 1/2 of an inch on the bottom here and the denominator here. And then the length of it would be the same as the length of side 1. So it would be 6 inches minus 1/8 of an inch minus 1/8 of an inch. So half of the thickness of both the top part of the top wall and the bottom wall. And then the last one would be for side 4. So side 4 is a quarter of an inch, and its length would be equal to 1/8 of an inch minus, 8 inches minus 1/8 of an inch minus a quarter of an inch. Okay. So if we added up all of these terms here, we can then plug them in we can substitute these in to this equation here, and we just multiply by all these known terms to determine the angle. Okay, so that's the general process for how you can determine that integral of d of s divided by t, the thickness as a function of s. Okay.
Side bottom.
Yes.
Why do we pull the constant length and then make it the inverse, like the 1 over 0.25 and the 1 over 0.5?
So just for the people in class can understand. So you're asking about this term here. Why is it like a divided by 1 over t by the thickness?
Correct.
Okay. So so in this integral, we are interested in so the thickness. So S represents the perimeter. So what we're doing here is from, I guess, let me call this point A here. So from point A to point B, our thickness is constant. So it does not change as a function of S. So since it's a constant, what we end up getting is we get the integral of ds over a constant value. Okay, so in this case, our constant value was 0.25 inches. So if you integrate for a constant, so if this is, let's say we were going, in this case, we were going from A to B here, we can bring out that constant from our integral, and we just get 1 over 0.25 inches, and we integrate from A to B of ds, which would just be equal to 1 over 0.25 inches, and the integral of ds just becomes AB.
Okay, great. Thank you for clarifying.
Yeah, no problem. That was a good question.